Hello children, today we will start the topic electric potential at a point due to an electric dipole. In the previous lecture, you learnt about the electric field at a point due to an electric dipole. And electric dipole was discussed in the lecture. So you know about electric dipole. Now we will be discussing about electric potential at a point due to an electric dipole. You also know about the expression for electric potential at a point due to a point charge. So let us discuss this. Let us consider an electric dipole constituted by two charges of equal magnitude and opposite nature, means minus q and plus q. Its dipole length is 12. The two charges are at points A and B. O is the midpoint. O is the midpoint of the dipole. We have to find the electric field. We have to find the electric potential at a point. As you got in case of electric field intensity at 2 points, on the axial position and on the equatorial position. Here again we will discuss electric potential at 2 points, one at the axial position and other at the equatorial position. Here AB is an electric dipole whose length is 12 and charge is minus q and plus q. So its dipole moment is P is equal to Q into 12. This is electric dipole moment of the given dipole. Here we will be discussing case 1. Case 1 when at a point on the axis of the dipole. Axis of the dipole. You see, this is the axis of the dipole. So let us consider a point P here on the axis of the dipole at a distance small r from the midpoint of the dipole. Now you find electric potential at P due to the charge plus Q at B is equal to 1 by 4 pi epsilon naught Q by this distance BP. This is equal to 1 by 4 pi epsilon naught Q by, you see this BP is equal to OP minus OB. OP is R, O is the midpoint of AB and AB is 12, so OB will be L. Means this BP can be written as R minus L, means this is R minus L. As electric potential is a scalar quantity, so it will have no direction. Now electric potential at P due to the charge minus Q at A. This is 1 by 4 pi epsilon naught Q by AP. Here you see it is a scalar quantity, so minus sign will be included in calculation, means this Q will be written as minus Q. This is equal to 1 by 4 pi epsilon naught Q by R plus L. This is R and this is L. This minus sign will be here. So these are the electric potential at point P due to the individual charges constituting the electric dipole. Now as it is a scalar quantity, so net potential at P can be obtained by adding them simple algebraically. Therefore electric potential at the point P due to the dipole is V is equal to VPB plus V PA. You see in VPB and VPA 1 by 4 pi epsilon naught and Q are common. So we can write it as equal to 1 by 4 pi epsilon naught Q common. This is 1 by R plus L and this is 1 by R minus L. This is minus. So VPB will be written first 1 by R minus L minus 1 by R plus L. 1 by 4 pi epsilon naught Q. Its LCM will be R minus L into R plus L. This will be R plus L minus R minus minus plus L. After then we will get 1 by 4 pi epsilon naught Q. You see R and R will be cancelled out. This will be 12. Q into 12 by R square minus L square. This is V. This Q into 12 is P, small p, dipole moment. So V is equal to 1 by 4 pi epsilon naught P by R square minus L square. For R very greater than L, this V will be 1 by 4 pi epsilon naught P by R square. So this is the expression for electric potential at a point P due to the given electric dipole. Whenever you are learning about electric field intensity, you learned that this position of P is called end-on position. Here again, the position of P is called end-on position or axial position. Is it clear? So this position of P, this position of the point P is called end-on position or axial position. Axial position. Understand? Okay, if you have understand this, now we will learn about the electric potential at a point on the equatorial line. So case 2. Case 2. At a point on the perpendicular bisector of the dipole. Point on the perpendicular bisector of the dipole. You see, this is an electric dipole. Here is point A, B, charge is minus Q, this plus Q, this is midpoint O, and the dipole length is 12. This is the perpendicular bisector. It can be in this side or it can be in this side. It can be in this side or it can be into the plane. So here we take a point P. You see, this is R and this is L because this is 12. Again, it is a scalar quantity, so we will not discuss about the sign of arrow or direction. Direction will be there if and only if it is a vector quantity, but it is a scalar quantity. So again, you find the electric potential at P due to these two charges individually and then add them by simple algebraic method. So electric potential at P due to charge minus Q at A is equal to minus 1 by 4 pi epsilon naught Q by, you see this distance is AP. This is equal to minus 1 by 4 pi epsilon naught Q by. You see, this is a right triangle. It is a hypotenuse, it is a perpendicular, it is base. So hypotenuse is the square root of perpendicular square plus base square, means r square plus l square. Electric potential at P due to charge at B. The charge is positive. So this is 1 by 4 pi epsilon naught Q by BP. You see this BP and AP are equal because this is L, this is L. So this is an isosceles triangle. It is equal to 1 by 4 pi epsilon naught Q by square root of R square plus L square. Here we see that two potentials VPA and VPB are equal in magnitude, but their signs are opposite. This is negative, this is positive. So therefore net electric potential at P due to the dipole is V is equal to VPA plus VPB. Whenever you will add these two, one is positive, other is negative, and they are equal, so their sum will be 0, means electric potential is equal to 0. Have you understand? Here you see the electric potential at equatorial position is 0. This position of P is called broadside on position. Broadside on position. Or equatorial position. Now see, everywhere the electric potential on this line remains same, means this line is an equipotential line, and if we will imagine a plane through this line, that will be called as equipotential plane. Another thing is that there will be no potential difference, means potential difference between any 2 points lying on the perpendicular bisector is 0. So note, you have to write it here, that work done in moving a charge from one point to the other point along the perpendicular bisector of the dipole is 0. Reason is W is equal to Q into V, as V is equal to W by Q or Q naught, and V is 0. V is equal to 0. That is potential difference between 2 points lying on the equatorial axis is 0, so there will be no work done along that. So this was the electric potential. Now there is a case when electric potential can be asked at a point which is neither at the equatorial axis, nor at the axial position. In that case, how will you do? So let us discuss about that. Electric potential at any point due to an electric dipole. Due to an electric dipole. See, this is an electric dipole with charges minus q and plus q, and this is a point P. The line joining the point P and the midpoint of the dipole makes an angle theta with the axis. This is point P. This is the distance. Take it A, take it B. This is L, this is also L, because AB is 2L. Now if we will increase this in this direction and draw perpendicular AL and BM on OP and PO produced, what will be the value of OM and OL? You see this angle is theta, so this angle will also be theta. So in the figure, you see this OM, this is base and this is hypotenuse, this is perpendicular. So OM, base is equal to hypotenuse into cos theta, means L cos theta. Similarly, OL is equal to L cos theta. OM and OL are L cos theta. Now let us find the electric potential at point P. Electric potential at point P due to charge minus Q at A. This is equal to minus 1 by 4 pi epsilon naught Q by AP. You see this AP. If this L is very smaller than this R, then PA and PL will be almost equivalent. Means PA will be equivalent to PL. So it can be written as minus 1 by 4 pi epsilon naught Q by R plus L cos theta. Similarly, VPB is equal to 1 by 4 pi epsilon naught Q by PM, which is equal to PB, or 1 by 4 pi epsilon naught Q by PB. Here PB is equivalent to PM. So this is equal to 1 by 4 pi epsilon naught Q by R minus L cos theta. So these are the electric potential at point P due to minus Q and plus Q respectively. Therefore, net potential at P. Therefore, net electric potential at P due to the dipole. The dipole is V is equal to VPA plus VPB. This is equal to 1 by 4 pi epsilon naught. You see Q can be taken as common. Q VPA, this is minus 1 by R plus L cos theta. Minus 1 by R plus L cos theta plus 1 by R minus L cos theta. 1 by R minus L cos theta. If we will expand it, simplify it, then we will be having Q by 4 pi epsilon naught. LCM will be R square minus L square cos square theta. This will be minus R minus plus L cos theta plus R plus L cos theta. 1 by 4 pi epsilon naught. You see R and R will be cancelled out. it can be q into 2l cos theta by r squared minus l squared cos square theta. It can be written as 1 by 4 pi epsilon naught. Q into 2l is p. So this is p cos theta by r squared minus l squared cos square theta. For r very greater than l, this v will be equal to 1 by 4 pi epsilon naught p cos theta by r squared. So this is the expression for electric potential at any point P due to the electric dipole. You can find the expression for electric potential at the axial position and perpendicular bisector by using this relation also. You see how. So when you will want to find the electric potential at a point on the axis, means case 1, when the point P lies on the axis of the dipole, on the axis of the dipole, then you see if P will be here, then this theta will 0, theta is equal to 0, and when theta is 0, cos theta will be 1, means V is equal to 1 by 4 pi epsilon naught P by r squared. This was the expression you directly obtained. Now, when the point P lies, case 2, when the point P lies on the perpendicular bisector of the dipole, then theta is equal to 90 degree, and when theta is 90 degree, cos 90 degree is 0, therefore V is equal to 0. So if you are asked to find the expression at a point due to an electric dipole, you can use this diagram and derive by that way. If you are asked to find the potential at some specific positions, then you can use the earlier method. In this lecture, you will be having the idea of these only. In the next lecture, we will be learning about the behavior of an electric dipole in the electric field. Thank you.